Hey there. Ever wonder why deep learning models, like the ones that power your phone's voice assistant or self-driving cars, work so well? It's not magic, it's math and a whole lot of clever optimization. Today, we're diving into a groundbreaking study that finally explains why algorithms like Atom can navigate the wild, non-smooth landscapes of neural networks and still find the best solutions. Let's break it down. Neural networks are like complex mazes. Each layer transforms data through mathematical operations, but here's the catch. When we use ReLU activation functions, those rectified linear units that act like tiny switches, they create a piecewise linear structure. Imagine a city with sharp corners, where the rules change abruptly at every intersection. This makes the lost landscape, the mathematical space the network navigates, super chaotic. Now here's the puzzle. Traditional optimization algorithms like Atom were designed for smooth, continuous landscapes. They assume gradual changes and no sudden jumps, but in ReLU networks those assumptions break down. The parameter space is divided into exponentially many regions, like a maze with billions of rooms. How does Atom even begin to find its way? The answer lies in two surprising mathematical tools, stratified Morse theory and Kakeya sets. Let's start with stratified Morse theory. Think of it as a way to map out the maze. Instead of treating the entire space as one big jumble, it breaks it into smaller, manageable layers, like a cake with different strata. Each layer has its own smooth rules, and the theory helps us understand how the optimizer moves between them. It's like having a roadmap for navigating the maze without getting lost. Now Kakeya sets. This one's a bit of a mind bender. A Kakeya set is a mathematical object that contains a line segment in every possible direction. Imagine a needle that can point in any direction. This set has room for all of them. The paper uses this concept to analyze how the optimizer sees the landscape. By leveraging Kakeya bounds, they show that the number of times the optimizer crosses between regions isn't exponential, which would be bad, but nearly linear in the effective dimension. That's a huge simplification. But here's the real breakthrough, the uniform low barrier ULB property. This means the lost landscape doesn't have big, insurmountable walls between regions. Instead, there's a smooth path, like a bridge between low-loss areas. This ensures that the optimizer can traverse the entire space without getting stuck, even in non-convex, non-smooth settings. And the best part? The authors prove that Atom converges globally without relying on smoothness or convexity assumptions. They show that even in these chaotic ReLU landscapes, the optimizer's steps are guided by mathematical guarantees. This isn't just theory. It's why your phone's voice assistant works, why self-driving cars navigate safely, and why AI models generalize so well. But here's the deeper question. How do these mathematical tools translate to real-world performance? Let's zoom out. Neural networks have millions of parameters, but they often end up in flat regions of the lost landscape, places where small changes don't drastically affect performance. This is where stability comes in. Researchers have shown that these flat regions are mathematically guaranteed under certain conditions, like the Polyak-Łojasiewicz (PL) condition. Think of it as a hill with a gentle slope. No matter where you start, you'll eventually roll to the bottom without getting stuck in a ditch. And let's not forget the role of optimization algorithms like Atom. They're not just random guesswork, they're guided by mathematical principles. By balancing learning rates, tracking gradients, and correcting biases, these algorithms act like a GPS, steering the network away from chaos. The key is the gradient Lipschitz constant, which acts like a speed limit. It measures how smoothly the model adjusts, ensuring it doesn't overshoot the optimal solution. So why does this matter? Because these mathematical guarantees mean we can trust neural networks to learn reliably, even as they grow more complex. It's the reason your phone can recognize your face, your smart speaker can understand you, and self-driving cars can navigate busy streets. But here's the kicker. Even in super complex networks, the gap between training and real-world performance isn't chaos. It's tied to two factors: the effective gradient dimension, the complexity of the problem, and the tiny step size after freezing. This means wide, deep networks aren't wild, unpredictable beasts. They're following mathematical rules that keep their errors in check. The takeaway: AI isn't magic, it's math with a side of discipline. These guarantees explain why models train reliably, even when the numbers get wild. Next time you see an AI doing something impressive, remember, it's not just luck. It's a symphony of constraints, careful steps, and mathematical safeguards keeping everything on track.